Now I want to talk about symmetry. So let me start off by talking about what symmetry is before we get into the details of what symmetry is for the Fourier series. So our definition is, excuse me, let me start this again. I'm going to begin talking about even symmetry. Now, it's really easy when we're talking about symmetry, about even symmetry, to confuse even symmetry of a function with being even as a number. Being even as a number just means that it's divisible by 2 evenly. But as a function, it means that that function of t is the same thing as it's the function of minus t. So the intuition here, what I want you to see in your mind's eye when we talk about even symmetry, is a signal like this. It's something that we can horizontally flip. Because fundamentally, isn't that what we're doing if we take our t and we replace it by negative t up here? We're just horizontally flipping it. Here's another example. Sabine, what's the name of this signal, of this function?
That'd be a cosine function?
Yeah, exactly. So cosine is even symmetry. And if we're taking a look at what that means for the Fourier series, let's drop back here to the Fourier series for a second and see that the Fourier series, this simple version of the Fourier series, is composed of cosines and sines. Cosines are even, sines are not even. If you've got a signal that's entirely even, then what does that say about its sum as being part of, how much of the stuff that's not even will it be composed of? Preston?
For what side?
Take a look at this definition of the Fourier series. And it's composed of cosines, which Sabine just said are an even function, and sines that are not even. So my question to you is that, let's say I ask you to find the Fourier series of this even function. Since this function is even, it's definitely going to be composed of cosines that are even. How much of these non-even things will go into composing this?
Isn't it after, so like the third frequency or whatever, or the third n would be composed of sine? Or is it?
You're memorizing something, but I don't want you to go by something that you're memorizing. I want you to go by reasoning. If we want to create this as a summation of cosines, and cosines are even. Cosines of different frequencies, right? So, maybe you've got a higher frequency cosine too, but things that are all even, versus stuff that's not even, like sines that do opposite things between plus t and negative t. So my question is that it's pretty clear that this arbitrary f of t, is going to have some components that will be cosine components. My question is, how much of it do you think would be composed by sines for whom values greater than 0 are the opposite of values less than 0, given the fact that this function does the exact same thing as time goes up as time goes down?
Then none of it.
None of it. And so just by pure reasoning, you've said that if you've got an even function, all your b sub n's will have to be 0. And that's correct. So as far as Fourier series goes, that means if f of t is even, that's the same thing as saying all of your b sub n's is 0. And you've cut down the work of figuring out what your Fourier series components are by half. Now you, whoops. That was weird. Now you just have to find your a sub n components, and you don't have to find your b sub n components. All right, let's talk about odd symmetry. So we'll firstly talk about the definition of what odd symmetry means. And the definition, the mathematical definition, is that f of t, for if it's an odd waveform, is equal to minus f of minus t. And the intuition here is you have a signal that looks like this. So you not only have to horizontally flip it, that's your minus t, but you have to also vertically flip it. That's the minus in front of everything. And it doesn't matter the order. Just convince yourself, I'll erase this in a second, this is just nasty scratch work. But if we horizontally flip this, then instead of it going down on the right, it's going to go down on the left. And then everything else is the same. So this is an example of this flipped left, right. And now if we flip it one more time up, down, to give us minus f of minus t, well, we still have this vertical piece here. But now instead of it, if we flip it up, down, this will start off at the bottom and go up. And of course, that's the exact same thing as we started off with over here. So that's why it's a odd symmetry. And there's one other common, very common waveform that has that odd symmetry. And you can see where we're headed with this already. It's this, which, Chow, what is this? What's the name of this waveform? This guy down here. So it's sinusoidal, and it goes through the origin. To the right, it goes up. To the left, it goes down. Give me a thumbs up if you can hear me, Chow. Okay. Okay, Tank, do you want to help him out?
It's going to be a sine wave.
That's a sine wave. And so by the same reasoning that Preston said earlier, if you've got a function that is odd, it'll be only composed of these odd portions of sines. You'll only have b sub n parts. You won't have any a sub n parts, because the a sub n is fundamentally even. So the So the intuition here, I'm sorry, not the intuition, the Fourier series issue is that if your function is odd, that means it's composed entirely of B sub n components and all the A sub n components are 0. Now, there are many other symmetries, and you can find them in your text. And I honestly don't find them all that helpful. There's half-wave symmetries. As we get into more and more detailed kinds of symmetries, the rules for determining their symmetry get more and more complex, and the impact on their Fourier series gets more and more complex. And at some point, it's easier just to simply figure out what the Fourier series is using the direct mathematical rules in this page over here. So if you're curious about seeing more symmetries, it's in the text, but you're certainly not required to know it for this class.